All right, today we're going to tackle one of the most misunderstood and, honestly, one of the most misused keywords in both C and C++, volatile. It's such a small word, but it carries a huge amount of weight. And, getting it wrong can lead to some truly baffling, pull-your-hair-out kind of bugs.
So let's just dive right in with a kind of weird question. We all think of our compilers as these amazing tools that help us, right? They make our code better, faster, stronger. But what happens when the compiler's attempt to be too clever actually introduces a subtle, really hard-to-find error? Well, this is the exact problem that Volatile was created to solve.
To really get this, you have to think about your compiler as this brilliant but very literal-minded assistant. Its main job, especially when you turn on optimizations, is to make your code run as fast as humanly possible. And to do that, it's always looking for any little shortcut it can take.
So, let's say the compiler looks at a super simple piece of code like this one. It analyzes the flow, okay? It sees you set a variable x to the value 5, and then you go and print x 2 times in a row.
Now, from its point of view, its logic is perfect. It's thinking, hey, I just went to the trouble of loading the value of x into a super fast little piece of CPU memory called a register. Nothing in the code I can see has changed it, so for that second print, why on earth would I go all the way back to main memory? That's slow. I'll just reuse the value I already have right here. It's efficient, it's smart, and yeah, 99% of the time, that's exactly what you want it to do.
But here's where that same logic just completely falls apart. Imagine your code is waiting for a piece of hardware to get ready. It's in a loop checking a status register over and over and over. But our smart compiler, in all its wisdom, checks that register one time, sees it's not ready, and assumes it will never change. Why? Because it can't see any code that changes it. So it optimizes your waiting loop into an infinite loop. Your program is now stuck. Forever. And this is where we, the programmers, have to step in and give the compiler a direct order. We need a way to tell it, hey, back off. For this one specific variable, your assumptions are totally wrong. And the tool we use to give that order is Volatile.
So at its very core, Volatile is both a promise and a warning to the compiler. It's you saying, listen, this variable is special. Its value can be changed by things outside of the neat little world of the code you're currently analyzing. We're talking hardware, an operating system interrupt, maybe even another thread. And this quote just nails the crucial distinction. As one developer put it, this is not a suggestion. It's not a hint. The compiler must obey. It's a command that forces it to throw its clever optimizations out the window for this specific variable, all to make sure the program is actually correct.
So here's the bottom line. When a variable is marked as volatile, the compiler is forbidden from caching its value in a register. Every single time your code even mentions that variable, the compiler has to generate instructions to go directly to its main memory location and fetch the latest, most up-to-date value. No more shortcuts, no more assumptions.
Okay, so let's talk about the specific, pretty narrow cases where this command isn't just useful, but absolutely essential. You see, overusing volatile is usually a sign of a problem, but in these specific scenarios, it's the only right answer.
There are really 3 classic places you'll see this. First, a variable that can be changed by an interrupt service routine. That's a special function that can just pop up and run at any time, interrupting your main code. Second, and this is super common in embedded systems, is for hardware registers. And the third is a more, let's say, obscure C feature involving setjump and longjump.
Let's try to make this a little more real with a quick story. Memory mapped I/O. It's just a fancy way of saying we make a piece of hardware, like a temperature sensor, look like a simple memory address to your program.
Now, as the programmer, your expectation is crystal clear. Every time you read from that special memory address, you're not just getting some number that's stored somewhere. No, you are actively poking the hardware to get a brand new live reading of the current temperature.
But without Volatile, our literal-minded compiler assistant comes back to haunt us. It reads the temperature once, sees 25 degrees, and thinks, okay, got it, 25 degrees. From that point on, it'll just keep reusing that same stale value, and your program will be completely clueless that the actual temperature might be soaring up or plummeting down.
Okay, now we have to talk about the single biggest, most dangerous misunderstanding about Volatile. This is a myth that has been the source of so many bugs in multi-threaded code.
I mean, it seems logical, doesn't it? You've got a variable, it's shared between two threads, it can change unexpectedly, so Volatile sounds like the perfect tool to make sure each thread always sees what the other thread did, right?
Wrong. Emphatically no. This is absolutely not what Volatile is for, and using it this way creates this false sense of security that is almost guaranteed to lead to disaster down the road.
This table really breaks it down. Look, Volatile only guarantees one thing. It stops the compiler from optimizing away your memory accesses. That's it. It does not guarantee that an operation is atomic, so something like x++ can still be interrupted halfway through by another thread. And this is the really crucial part. It does nothing to stop the hardware, the CPU itself, from reordering memory operations for performance. That means you have absolutely zero protection from data races.
As one of the developers in our source material so wisely put it, you can't just sprinkle Volatile on your multi-threading problems and hope they disappear. It is not a magic band-aid for concurrency.
So if Volatile is the wrong tool for synchronizing threads, then what's the right one? Well, fortunately, modern C and C++ have given us much better, much safer, and way more explicit tools for this exact job. In C++, the answer is std atomic types. In C, it's _atomic. These things are designed from the ground up for concurrency. They give you the guarantees about atomicity and memory ordering that Volatile never could. And for more complex stuff, you should be using proper tools like mutexes. And look, this isn't just a matter of best practice anymore. The C++ language standard itself is making this official. As of C++20, many of those old, incorrect ways people used Volatile for multithreading are being formally deprecated. The message from the Standards Committee is loud and clear. Stop using it for this.
So let's just wrap this all up. Remember, Volatile is a command. It tells the compiler to back off with its optimizations. Its real use cases are very narrow. Think hardware interaction, memory-mapped I/O, and variables touched by interrupt routines. It is absolutely not a tool for synchronizing threads. For that, you have to use atomics and mutexes. End of story.
And that really leaves us with one final thought. Our tools, our compilers, they're getting smarter and smarter every year. But Volatile is this powerful reminder that at the end of the day, we, the programmers, are the ones in charge. So it forces us to ask, how do we make sure we understand our tools well enough to command them correctly, instead of just trusting their smart behavior blindly?